Hello and welcome to the homework tips video for homework number 8 from Astronomy 10. Okay, so we have two problems here that relate to Earth as a planet. Both of these problems do not have a unique formula associated with them, no new formula that we're using in the chapter. Instead, they're just based on common physical principles. Okay, number 1 is going to be all about volumes, and number 2 is going to be about calculating movements based on the values that we were given. Okay. So let's take a look at volumes in problem number 1. Okay, so in problem 1, what are we told? Well, we're told that we have the planet Earth, and we're given some real information about Earth. We're told that it has a diameter of 12,756 kilometers. We're given the mass of Earth as well, that's its total mass. And then we're asked about a couple parts of the Earth, specifically the atmosphere in part A, and the mantle in part B, okay? Now, I could have asked about other parts of the Earth, but actually we're not really sure about the density of the inner core or the outer core. It's really anyone's best guess, but we have a better idea about the density of the atmosphere on average. We know that quite well because we can measure it directly. And as far as the mantle, although we can't actually dig through the crust and get to the mantle, humanity has never done that, we still have a pretty good idea of what the density of the mantle is based on the material that comes up from the mantle in terms of volcanoes and so on. Okay? So let's draw a quick sketch of the Earth here. So this is going to be not exactly to scale, but it's going to highlight some of the scales. So here we have the Earth. All right, let me make that a circle. Okay, and we're going to concern ourselves with the mantle. So that's going to be one part of the problem. That's going to be in part B. So this is going to be, we'll call this R for the mantle. And then we have the atmosphere. Now the thickness of the atmosphere is really tiny. So I'll call R for the A for the atmosphere, and draw it smaller, but it's even much smaller than that to scale. We have a very thin atmosphere as compared to the overall radius of the Earth. Okay, so in part A, what are you asked to do? Well, you're asked to find a proportion of mass, and it's the same thing in part B. So we're given the density of the atmosphere at 1 kilogram per cubic meter, and then we're also given some dimensions. We're told that it extends from 100 or extends to 100 kilometers above the surface. Okay, so that means if we look at RA, all right, well, RA is a distance that is 100 kilometers, okay? So we definitely know RA outright, but we need to actually find the volume based on our values here. So we need to find the volume of this yellow region that, representing the atmosphere there. So how do we go about doing that? Well, we subtract the outer volume that's at the top of the atmosphere. So that basically, the volume at this point, okay? So we subtract from it the volume of the actual solid planet, because that will just give us the volume in between, which is the volume of the shell that is the atmosphere, okay? So it's a volumetric shell. So how do we go about doing that? Well, the volume of a sphere is 4/3 pi r cubed. So if we need to find the volume of a shell, because the atmosphere is a shell here, okay, with a defined thickness, it's going to be 4/3 pi, and then r plus ra cubed, because that would be the radius of the Earth, I'll put an e there, plus the additional height of the atmosphere, minus just re cubed, okay? And that will give you the volume of the sphere, because we're just subtracting the volume of the shell, because we're just subtracting one sphere from another. To show the intermediate step here, let me show you that, because that's going to be kind of where you're going to get. You would just take 4/3 pi re plus ra. I should call that ra both cases. All right, so ra right there. So that's because that is this total outer sphere. Obviously, I'm just drawing a 2D section here in my notes, but imagine there's a large sphere that includes the atmosphere. And then you subtract the inner actual terrestrial sphere, the solid Earth, which would just be 4/3 pi r Earth cubed. And make it clear in the image, our Earth goes from the center up until where the atmosphere starts. Okay? And then all I did in this step that I showed first was factor out the 4/3 pi, because it's shared by both terms. Okay, so that's how you calculate a volume of a shell in general, and specifically for these values resulting to the atmosphere. Once you have that volume calculation, you need to find the mass of the atmosphere. Okay, so the mass of the atmosphere is just volume times density times gravity. Okay, so well, that would be the force. Excuse me. In this case, you just want the mass, so it's just volume times density. Okay, because we don't care about the gravity bit. We are not trying to calculate a weight of the atmosphere. We just want its mass. So V times density. Okay, and in other words, that's going to be the volume of the shell that you calculated times the density of air. Okay, which is this value right here, the 1 kilogram per cubic meter. The air is not very dense on average. This is actually the densest value at sea level. It gets less dense as you gain elevation above the surface of Earth. So this is a generous estimate. So you should actually get yes, a large mass in terms of everyday masses, but compared to the overall mass of the Earth at 5 trillion kilograms, because 10 to the 24 is a trillion trillions, then, well, you should get a small percentage. And that's what I asked for here, a percentage of the total mass of Earth. So whatever value you get for m, you're then going to get the percentage by just taking the mass of the atmosphere over the overall mass of Earth as given times 100. Okay, that should give you a small percent because the atmosphere does not make up a lot of the total mass of Earth. But what about the mantle? Well, the mantle is the same procedure. You're still going to calculate the volume of a shell. All right, in this case, the shell is going to be the shell of the mantle. I'll sketch that for you real fast, right? So that's going to be basically this region here, and we imagine it's a spherical shell, so it's a sphere with a hole in the middle because you're subtracting out the region in the middle, okay? And you're just going to use the density given, all right? Now, the interesting thing about this is you have to do a couple of steps here. So one is you're told that the mantle extends from a depth of 70 to 2,900. So what I haven't actually shown in the figure is you do have to subtract an extra little crust piece. All right, so right around here is the radius of the crust, which is small. It's about 70 kilometers, okay? And you're going to subtract that in order to get your RM. So to draw it a bit more accurately, let's go ahead and erase our RM vector here. I think this will help you understand what we're doing. And we're going to, gotta actually erase it. There we go. All right, so we'll show that RM, the radius of the mantle, just goes from that 70 kilometer depth, which is relatively small, to a much greater depth of what I think was 4,000, or no, excuse me, 2,900 kilometers. Okay? Okay, so how do you go about doing that? Well, we have to take the overall radius of the Earth, and then we have to then consider the two subsequent steps here. We're just trying to find the volume of the shell. Okay? So if we think about it, we could take the volume of the shell as the volume of the outer mantle minus the volume, and these would be spheres, of the inner, and we'll just call this the core. All right. Okay. So those are both sphere volumes, as I said. So then the outermost one would be our 4/3 pi. And then here, you would take the radius of the Earth minus the 70 kilometers. Okay, so radius of Earth minus 70 kilometers. Okay? And one thing is if you want these volumes to be in units that you can multiply by density, because notice the densities are given in base units, kilograms per cubic meters, both of them are. Okay? No worrying about grams or anything, just kilograms per cubic meter. But all of the distances, like the RE and the radius of the atmosphere, RA, that we talked about in part A, or over here, the 70 kilometers, those are all obviously in kilometers. Well, you can't leave them in kilometers, you have to convert them, excuse me, that should be a 3, you have to convert them over to meters because otherwise you cannot multiply by density. So all your volumes are going to be cubic kilometers, but you have to convert to cubic meters. Make a little note there. So convert to cubic meters. Okay, and it's going to be the same for part B. That note applies as well. So we got our outer radius for finding our volume of our mantle shell, and then we subtract the inner radius, which will be 4/3 pi, and in this case, it's just going to be RE, and then minus, in this case, we want it to go all the way down, so we need to minus the 70 plus the 40, plus the 2,900, because we just need to get that remaining piece. So it would be 70 kilometers plus the extra depth much greater depth of 2,900 kilometers. Okay, and of course that's all going to be cubed. Okay, so that's how you're going to find the volume of that inner shell, which is the mantle. Okay, and then obviously to find the mass of the mantle, we'll call that mm. That's going to be the volume that you found times the density of the mantle. So the volume of the new shell specific to the mantle times the density of the mantle. And the mantle is much, much denser than the atmosphere. It's 4,200 times denser. It's about 4 times denser than water, which makes sense. It's rock, all right? Somewhat liquefied rock in many parts. And so this one should make up a relatively large percentage of the total mass of Earth, because you'll do the same percentage calculation, but obviously with the new mass, down for part B, and then you should be done. Okay, so enough about number 1. Let's briefly talk about number 2. Okay, so number 2, we're given a couple of pieces of information. We're told that over the entire Earth, there are 60,000 kilometers of active rift zones. That's where the oceans are spreading apart and new oceanic plates are being created, with average separation rates of 4 centimeters per year. Okay, so that's another bit of information you'll need. So question A is about area. How much area of new ocean crust is created each year over the entire planet? Give your answer in both square meters and square kilometers. Okay, and this area is approximately equal to the amount of ocean crust that is subducted, since the total area of the oceans remains about the same. All right, so as new crust is created, new oceanic crust is created on the edges of the continents, that crust is being pushed underneath those continental plates, getting remelted. So it's a constant process. Okay, all right, so to actually do the calculation here, what you want to consider is you have some rift. Okay, so this is our 60,000 kilometer rift all combined into one. All right, that rift has a certain length. Okay, so that's our 60,000 kilometers. And that rift is spreading apart at a certain rate. All right, so the rate is the 4 centimeters per year. Okay, and as it spreads apart, new area is created. Okay, and so you simply want to calculate this area here. Okay, well, area by definition is length times width. Okay, well, and the width here is defined by the rate. Okay, because the width is going to be velocity, rate times time. Okay, so it's going to be the length, the 60,000 kilometers that's given, and then we're going to replace the width with just velocity times time, because velocity multiplied by time gives us distance. Okay, so it's going to be our rate and then multiplied by time t. And what's the time that's given? All right, well, each year. All right, so what's great then is you could actually leave your rate in 4 centimeters per year, not even convert it to seconds, leave your time also in years, and your years will cancel out. Then your only concern is that you'll have seconds for your value of, centimeters for your value of width, and your length will be in kilometers. So you want to convert those both to meters to get a final answer in square meters, and then convert them both to kilometers to get a final answer in square kilometers. Okay, so that's it for part A. All right, so I'm going to shrink this a tad so I can show you the last step for part B of number 2. Okay, so for part B of number 2, you're just introducing actual volume of plate that's being created. Let's see what we have here. So we're told in part B, what is the volume of new oceanic basalt added to, because that's the crust is made of basalt, added to Earth's crust each year? Give your answer in both cubic meters and cubic centimeters, okay, or cubic kilometers, excuse me. All right, so because just like in part A, I wanted in meters and kilometers, here I want in cubic meters and cubic kilometers. Assume that the thickness of the new crust is 5 kilometers, okay? So it's the same idea. The only difference now is you're considering the actual thickness and you're creating a volume like this, all right? And so then this thickness, which we will call, I don't want to call it T because we already use T for time, so we'll call it big T, all right? And we know that that thickness is defined as 5 kilometers, okay? So then to find the volume of crust that's created, and by the way, this was the area of crust. All right, so really similar results. So volume of crust, okay? So volume of crust in this case would be length times width times thickness. We can do the same thing with width, because width is the only variable that's actually dependent upon the rate of the expanding plates. So we just replace the width with the rate times time and leave the length of 60,000 kilometers and the thickness of 5 kilometers as fixed. And that will give you a volume. And make sure you report that volume in both cubic meters and cubic kilometers. And finally, in part C, what percentage of Earth's entire volume does this annual addition of new material represent? Well, for C, you then would simply want to take a ratio of the volume of crust created over the volume of Earth using the 4/3 pi r cubed. It's not a shell because you're taking the entire volume of Earth, not unlike when we were considering the entire mass of Earth. But you do have to actually calculate the volume. I don't give you the volume, but you can easily calculate it with the information you were given in part A, namely the diameter of Earth. Okay? All right, and then you take the ratio of those two volumes, multiply by 100 to get the percentage of actual crust that's created as the percentage of the overall Earth volume. And this one should be a small percentage because anything that happens on the surface of Earth is tiny compared to phenomena happening in the interior of Earth because there's so much more interior space than surface space. Okay, so that concludes the tips for homework 8. Thank you so much for watching.